In this short section, we want to take a look at what's called numerical integration. Let me share my screen with you because it will be important later on that you be able to see more closely what I'm looking at. I can get it to share. There we go. Now, you're looking at my lecture notes for this section, which are actually super short. They're about a page and a half. I know you're all cheering out there because really, I don't make my students do numerical integration by hand very often. I used to, but now that computers are so much more powerful, and we're using programming so much more often in mathematics and engineering, it makes more sense to do this with a computer. And so in my classes, we explore numerical integration by writing a Python program. We'll talk about that in the next video. So if you're interested in Python programming, you can watch the next video. I don't expect my students to know anything about programming or Python. I work through it with them and they learn how to program as part of the class. In this video, however, we just want to give the background for why numerical integration is important. We've learned a lot of different techniques of integration. We've done integration by parts, trig integrals, of which there were many types, trig substitution, partial fractions. In the last section, we were taking a look at using the integral tables and also computer algebra systems. This is fantastic stuff. It lets us integrate all kinds of things. But the fact of the matter is the vast majority of functions simply cannot be integrated. In other words, there is no known antiderivative for them. What do we do in that case? In other words, we've got a function, but we don't know how to write down the antiderivative. Now, sometimes that's because we don't know how to write it down in terms of the elementary functions. Now, what do we mean by elementary functions? By elementary functions, we mean the ones we can write down. That would be polynomials, other kinds of algebraic functions like radicals, rational functions, logarithms, exponentials, even tower functions we can write down. Remember, tower functions are a variable raised to a variable power. So the variables in the base and the variables in the power. But still, we can write those down. These are what we would consider to be elementary functions. But sometimes the antiderivative can't be written in terms of these things. We simply can't write it down, even if we know it exists. Sometimes we don't know whether it exists or not. And sometimes we know it exists, but we don't know how to write it down. With an indefinite integral, we're truly stuck when this happens. I mean, we're dead right out of the water, right? We can't do anything for an indefinite integral because we're looking for the antiderivative function. We don't know how to write it down, we're stuck. Now, some of these show up so often in different kinds of applications that we've given them a name so that we can represent them. The error function is one of them, and it's written ERF of x, and it's represented by this right here. And you may look at that and go, well, okay, the 2 divided by the square root of pi, that's just a constant. So I don't have to worry about it. It looks complicated, but it's just a constant. And this, of course, is coming from the fundamental theorem of algebra, where we're taking the integral from 0 to the variable x of e to the dummy variable t squared dt. So really what we're trying to integrate here is e to the x squared. Well, unfortunately, I mean, that sounds pretty simple, right? The integral of e to the x squared. But we can't integrate that. We don't know how to write down the antiderivative for that. You would normally think of u substitution where u was x squared or t squared, but then you would have 2t or 2x as the derivative of u, and you don't have a t or an x in the integram. We're stuck. We can't do anything. This comes up so often that we've given it a name. It's called the error function. Now, I don't make my students work with the error function. That's for a statistics class or probability or something having to do with telecommunications, where it comes up quite a bit as well. In general, if we don't know the antiderivative, the best we can do is approximate the definite integral. And that's really what we want to talk about when we talk about numerical integration. We're not talking about trying to come up with an antiderivative function. We've already established that we can't. What we try to do instead is approximate the definite integral. Now remember, this is fundamentally different from the indefinite. The indefinite integral is giving us an antiderivative function, but the definite integral is giving us the area between the curve and the x-axis. So we should be able to approximate that with a definite integral. Now the problem is, in order to use the fundamental theorem of calculus, we need to have an antiderivative, and if we don't, we're kind of stuck. So what we've done is we've come up with some methods of what are called numerical integration that approximate the area under a curve. Now you already know two of them for sure, the left Riemann sum and the right Riemann sum. And hopefully you also learned the midpoint Riemann sum, but I have them open on Desmos in case you have not. So let's review what these Riemann sums are and how they are methods of numerical integration. So we're going to start with the right Riemann sum. Now this is basically on this function that you see up here. It's a polynomial expression with a constant of 1/18 at the front. The 1/18 is just to keep the sizes low so that I could see it all on one screen. And you can see that this is going from, it's hard to tell, but it looks like -7 to 6. So it's integrating over this region. Part of it is above the x-axis, parts below. The part above is shaded in blue and the part below is shaded in red. A right Riemann sum draws rectangles from the lower limit of integration, the vertical line representing the lower limit of integration, to the vertical line representing the upper limit of integration. And it uses the right endpoint of each subinterval for the height of that rectangle. And then we take the area of all the rectangles, we add them together, and that becomes our approximation for the area under the curve. And again, a right Riemann sum is using the right endpoint of each subinterval to calculate the height. Now, you can tell here that on this particular one, I am going from -7 to 6, and I have 44 boxes or 44 subintervals. If I make fewer boxes, if I decrease this somewhat, you can tell that the approximation is not as good. There's more white space that you see right here. It's not as close to the actual shape of the curve. And that white space indicates an error, an underestimation of the error area. And then these parts right here where it's past the curve are an overestimation. So generally speaking, if I'm using a right Riemann sum and I have an increasing function, I'm overestimating the amount of area. And if it's decreasing, then I'm underestimating the amount of area. Now, this was the right Riemann sum that you learned in Calculus 1. What about the left Riemann sum? The left Riemann sum is basically the same thing. Let me reduce the number of boxes so that we can see the boxes more easily. You can tell on this, it's very similar to the right Riemann sum. It's the same function, in fact. But in this particular one, I'm using the left endpoint of each subinterval for the height of the rectangle. So all I'm doing is I'm taking the width of each box, that's right endpoint minus left endpoint divided by the number of boxes, or b minus a divided by n. That's the width of each subinterval. Now, technically, they don't all have to be the same size as long as the widest one is approaching 0. That will give me the exact area under the curve as n goes to infinity, right? That's the definition of the definite integral. It's the limit as n goes to infinity of this Riemann sum. But in fact, if I don't know how to represent the antiderivative, then I can't use the fundamental theorem of calculus, but I can still use the left or right Riemann sum to approximate the area under the curve. So in other words, it's just an approximation, but it can be as close as I want by taking more boxes. The more boxes I take, the closer the approximation. On an increasing part of the curve, a left Riemann sum underestimates, and on a decreasing curve, the left Riemann sum overestimates. So it's the opposite of the right Riemann sum. This is another method of numerical integration that we could use to approximate, for example, that error function, e to the x squared. We could graph the curve of e to the x squared, draw a bunch of rectangles, add up their areas, and we'll have an approximation for the area, an approximation for the definite integral. We're totally lost on an indefinite integral because we don't know how to write down the antiderivative, but we can come up with an approximation for the definite integral. What about the midpoint Riemann sum? When we look at the midpoint Riemann sum, we're not using the left side of the subinterval or the right side of the subinterval for the height of the box. Instead, what we're using is, as the name suggests, the midpoint. So in this case, let me reduce the number of boxes to something where I can see it more easily. Now you can see more easily that this point right here is representing the midpoint. So on an increasing function, I can tell it's a little bit over and a little bit under. So this is the beauty of the midpoint Riemann sum. It is better than both the left Riemann sum and the right Riemann sum, because on each individual rectangle, whether it's increasing or decreasing, it's overestimating a little bit and underestimating a little bit, which means that this error kind of balances itself out, which means that the midpoint Riemann sum is one of the very best methods of numerical integration that we learn in basic calculus. Now, of course, there are better methods out there, but midpoint is really extremely accurate. So you can find the amount of area under a curve, even if you can't find the antiderivative function, by approximating using the midpoint Riemann sum. Now, there are two other methods that you did not learn in Calculus 1, and these are the two methods that we talk about in Calculus 2. In my class, we program these into a Python program. But what I want to do is go ahead and discuss them with you now. The first one is called the Trapezoidal Rule, and the second one is called Simpson's Rule. Let's take a look at what the Trapezoidal Rule does. In the Trapezoidal Rule, instead of using a rectangle, what it does instead is it uses a trapezoid. Now, this first trapezoid is kind of, well, not a great one. In fact, I'm not liking it a whole lot. If I can find the value, I think I'll move that left endpoint from being at 0 to being at 1. There we go. Now it looks much more like a trapezoid to me. It was kind of what I would call a degenerate trapezoid, or a trivial one. Now, what is a trapezoid? Well, when I think of a trapezoid, I think of the circus, and I think of that thing, that shape that elephants stand on. I don't know why, but in my head, for some reason, that just says trapezoid to me. So let me draw a picture of a trapezoid for you, and then we'll talk a little bit more about it. All right, so we're talking about Simpson's rule and the trapezoidal rule. So when we think about a trapezoid, remember that the elephant stands on something that looks like this and is actually round. But from the side, it looks like this. Now, what makes it a trapezoid? You have two sides that are parallel. So the top and the base are parallel. And you have two sides that are not parallel. Now, the one that the elephant stands on to make it structurally strong has flared sides, both of them going out. But that's not actually required. All that's required of a trapezoid is two parallel sides, precisely two. That doesn't mean two pair. It means exactly one pair of parallel sides and the other pair aren't parallel. So let's go back to our picture and let's see if we do, in fact, by that definition, have trapezoids. So the two parallel sides are the vertical line segments extending from the x-axis straight up to our curve. They're definitely parallel. These sides right here are definitely parallel. That makes this top and this point right here not parallel to the base. The base is along the x-axis, so it's horizontal, but you can see this top is slanted. It's not parallel to the base, which is along the x-axis. And that makes this shape right here a trapezoid. Now, this one next to it is also a trapezoid. It's harder to see, because it is so small or so close to the curve. So I'm going to blow it up a little bit so that you can see it a little closer. What's happened is we've divided this into 3 regions, 3 boxes. And instead of connecting at the height of the left endpoint or the height of the right endpoint or the height of the midpoint, we're just connecting the left side and the right side with a straight line segment. This makes it a trapezoid. Now, how do we find the area of it? Well, it turns out that the area of a trapezoid is the average of the 2 parallel sides, what are called the bases, and then times the height. Now, what's the height? The height of the trapezoid. Let's go back to our Word document here. So this is base 1, and this is base 2. And this length right here is the height, all right? So basically what we're doing is we're averaging the lengths of base 1 and base 2 as if we were forcing this trapezoidal shape to take on a rectangular shape. So the area of that trapezoid becomes the average of the bases, base 1 plus base 2, times the height. And that's basically giving you what would have been the area of a rectangle if it were rectangular. Like you chop a little of this off and stick it over here, you can turn it into a rectangle. And that's what we're doing, averaging the bases that are parallel and multiplying by the height. Notice that the height is perpendicular to the 2 bases. Well, let's go back to our picture over here and recall that this side and this side are the bases. And the side that's perpendicular to it, well, hello, that's the segment along the x-axis. In other words, this is my delta x. So to find the area of this one trapezoid, I'll take the length of this side, which is the function value at the left endpoint, and the function value at the right endpoint, add them together, divide by 2, and then multiply by delta x, which is the height of the trapezoid turned sideways. This gives us a formula for the area under the curve when we add all the trapezoids together. Now, you can tell that this is slightly better, probably, than the left Riemann sum and a right Riemann sum. It is not as good as the midpoint, surprisingly. And typically, the midpoint turns out to be better. But you can tell over here that if sections of it are roughly linear, then the trapezoid is really, really good. It struggles where there's a large change in curvature. Remember, we studied curvature in Calculus 1. So it struggles more in those particular cases. If we increase the number of trapezoids, we can increase the accuracy of our approximation. And you can see that it's getting closer and closer to the actual shape. It still struggles where there's more curvature, but on the parts where there's less curvature, it gets very, very close. And this will give us an approximation for the area under the curve. So let's take a look now at what the formula is for the area under a curve using the trapezoidal rule. So using the trapezoidal rule, we might have the sum of n trapezoids, and it ends up being 1/2 delta x times f of the left endpoint, f of x naught, plus 2 times f of x1, plus 2 times f of x2, plus so forth, 2 times f of x3, plus 2 times f of x sub n minus 1, the second to the last one, plus f of x sub n. Now, why do the first on the far left and the last on the far right only get counted once? And what's with the 1/2? Well, the 1/2 is coming from that average of the bases, right? We're averaging the lengths of the 2 bases, as we saw in this formula up here. So that's where the 1/2 is coming from. The h represents our delta x that you see here. So why is this only present once and this is present once? And why are all the ones in between present twice? Let's go back to the graph. Well, when we're looking at this right here, notice that the point on the far left only gets used on the first trapezoid. It never gets used again. And the one on the far right is only used on the trapezoid on the far right one time and never gets used again. But this point right here gets used twice. It is the right endpoint of the first trapezoid and the left endpoint, the second trapezoid. So all the points in between the first and the last get used twice, which is why they show up in the formula 2 times. This gives us a way of approximating the area under a curve, which is the definite integral. Now, this, as we said, is not as good with these curved sections where there's lots of curvature. So you might imagine it's not so great for something that's based on sine or cosine, when you've got lots of curvature going on. And this is where Simpson's rule comes in. So let's take a look now at Simpson's rule. Now you can see a Desmos program which has been created to illustrate how Simpson's rule applied. Now, this is a function sine x plus sine of 2x plus sine of 4x, lots of sine functions involved. And as you can see, it's very curvy, right? Lots of curvature here. Neither the left Riemann sum, right Riemann sum, or trapezoidal rule would be a great one for this one. The midpoint is still good because even though there's lots of change in curvature, it averages out the error on each individual box by overestimating a little and underestimating a little on each individual box, on each little segment. How does Simpson's rule then work? Simpson's rule says instead, well, if you've got a function that's got a lot of curvature in it, then why use a flat top? Like in the Riemann sums, the left and the right and the midpoint, you're using a flat top. And on the trapezoidal, you're using a slanted top. And it says, why do that? If there's a lot of curvature, why not use a curve to approximate one edge of the, quote, rectangle? It's not really a rectangle anymore. In other words, what they've done is they've taken 2 of the subintervals side by side, not 1, but 2, and they've approximated the 3 spots on each of the subintervals, the left, the middle, and the far right. So you're required to have 2 subintervals to give you the 3 points. And it's finding the parabola that goes through those 3 points. So it's going to approximate the top with a parabola instead. And there's a formula, can actually be computed using only algebra, no calculus techniques required, that will give you the area then underneath the parabola, between the parabola and the axis. So you can actually compute this area here using algebra. Now, I'm not going to go through it because it's about a 30 to 45 minute derivation, if not longer. But you can find it out there on YouTube if you want to look for it. Now, notice that because Simpson's rule requires you to have 2 subintervals side by side, that we're required to have an even number of subintervals. You can't have 3 or 5 or 7. You have to have an even number. So if we move this over a little bit, we can take a look at a different one of the subintervals, and we can see that the top is calculated on a different one. So let me get K to move over to the second one. Now you can see that we've moved over from the first pair of subintervals, we've moved to the second pair of subintervals. We have a far left, a middle, which is at the, in between the 2 subintervals, and then the far right. And then we can compute using algebra, just algebra, the parabola that goes through those 3 points, and we can use the parabola top to compute the area between the curve and the x-axis. This makes a little bit more sense if the graph is very curvy, like it depends on sine or cosine. When there's lots of change in curvature, it makes more sense to use something that's curved for the curved side of the box. And that's what happens here. And then, of course, we can take a look at the last one, which is k equal to 3. And again, we've taken the next pair of subintervals, the left point, the midpoint, and the right point, point, and we've computed a parabola that goes through those 3 points, and then we find the area between the parabola and the x-axis. Now there's a formula that does this. The derivation is quite long, and I'm not going to go through that, but this is the formula right here. It does have a very repetitive pattern. There's a 1/3 at the front. Delta x is the length of each subinterval. There must be an even number of subintervals. The left endpoint is only used once on the first pair, and the last one is only used once as well. Notice that there is a repeating pattern for the ones in between. It's 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, and then back to 1. So it has to have the right number so that it both starts with a 4 and ends with a 4. And this will compute an approximation for the area under the curve with a parabolic top. Now, it sounds crazy that it could be this simple. I know it doesn't look simple, but if you think about what you're doing and computing a parabola going through 3 points and then finding the area between the parabola and the x-axis, this is a pretty simple formula. And this formula will give you an approximation to the area under the curve. So this is what we mean by numerical integration. We are approximating a definite integral, the area between a curve and the x-axis, from a given x value to another given x value, using either a left Riemann sum, a right Riemann sum, a midpoint Riemann sum, the trapezoidal rule, or Simpson's rule. I hope this makes sense to you, and if you're interested in Python programming, join me in the next video where I walk my students through the Python program, which focuses on the trapezoidal rule and Simpson's rule.